This is Jamie Pittman, and this is my Lab 1 for constant velocity. Video overview. So we'll go through the introduction, then the models, then the experiment, coding, the results, and then the discussion/conclusions. The main purpose of this lab is to observe an object moving at a constant velocity with no net force to a computational model. The main physics principles used in this experiment are Newton's first and second laws and the constant velocity. Newton's first law states that an object in motion stays in motion unless acted upon by an outside force with no net interactions. Newton's second law is an object's acceleration is directly proportional to the net force acting on it and inversely proportional to its mass, as seen as F equals ma. Constant velocity is just when an object stays in constant velocity with a zero net force. The velocity update formula is v final equals v initial plus f net over m times change in t. But since the net force is equal to zero during the constant velocity, that would just cancel out, and we would find that the final velocity equals the initial velocity. And for the average velocity, we can find that just by looking at the slope of the graph. And the position update formula is just used to update the position of the glider along the track at each time interval. And so these are the results we get from the experimental model. So you can see that it's not perfectly straight, which is just due to the fact that human error, and it's just a real life experiment, so it wouldn't be perfectly straight because of like all those outside sources. Experiment system and surroundings. The system was a glider on the track. The surroundings would be air resistance and friction, and the track. And the experimental position would be tracker, and we found the predicted position using GlowScript, and we put the results into Google Sheets. The procedure was we recorded the glider moving along the track at a constant velocity. We uploaded the video in the tracker, and then we used the starter code in the GlowScript to make a computational model and put the results into Google Sheets. So this is what it looked like in tracker. We had the glider moving along the track, and we let it go the length of this meter stick, which was approximately 1 second. And so it gave us these two graphs, but we can ignore the y position by time gap because we're just looking at the motion in the x direction. And then it gives us this chart with the data points. For the initial velocity calculation, I just took the final position minus the initial position over the time it took to get there, and we got about 0.8 meters per second. And as you can see, we start at time equals 0 and 0.18 meters. The GlowScript initial conditions, so we just plugged in the same values, so it started at 0.18 meters and it was about 0.8 meters per second for the velocity. And we started at time equals 0, and the size of each time step was 0.033 for the frames per second. And the whole clip length was about 1 second, and there was zero net force on the ball, or the glider even. And then we used the velocity update and position update vector or formulas to determine what the ball was at each time step. And this is what the computational model looked like. So it's a straight line because it was a perfect experiment, obviously. And then these are the two lines compared to each other. So they're pretty close. They both show a linear trend with roughly the same slope. However, the slopes do begin to differ because, one's the perfect computational model, one's a real life example. They both start at 0.18 meters and end at roughly the same place, but around 0.1 seconds the lines start to separate and we can see a difference in the slope. Possible sources of error include friction and air resistance. So it's supposed to be on a frictionless track, but obviously there's still going to be friction in a real world example like this. And air resistance, obviously, as it's moving through the air, it encounters that resistance and it slows it down. And human error, there's human error in every real life experiment. What if and what does it mean? What if the axes were flipped? This would just mean that the sign would flip and the slope would become negative. However, the magnitude of velocity would remain unchanged. The position versus time graph would also remain constant and wouldn't change. And the net force would still be 0 either way. Are we able to tell how many forces are being added together to give a net force of 0? No, because we don't know how many pushes or pull occur, because everything is still balanced out and there's still constant velocity in the x-axis. Conclusion. We were successfully able to conclude that Newton's second law was supported throughout this experiment because our expected and actual results were very similar. This means that we can assume there was a constant velocity with 0 net force throughout the whole experiment.